In this problem, we're given the derivative of a vector-valued function, r of t, and we're supposed to find the actual function r of t. Now remember from Calc 1, the way we do this with good old regular old functions, when we have the derivative of a function, we want to find recover the original function, we take antiderivatives. We take an antiderivative, and the exact same thing will be done here. So again, we have a derivative of a vector-valued function. So then the original vector-valued function, r of t, is the antiderivative of dr dt with respect to t. And if you think about how the derivative of a vector-valued function is just the derivative of each of the components, it makes sense that the antiderivative of a vector-valued function is just the antiderivative of the components. So this is like so. And now we'll just find each of these antiderivatives individually using calc. This is a Calc 1 problem here. This is a Calc 2 problem. We'll use integration by parts. So let's start with the Calc 1 problem. Right, remember that, let's see, 2t dt. Right, this is 2t squared over 2 plus some constant. I'm going to use the constant d because I'm going to use the constant c for this one. And I just want them to go in alphabetical order. There's no real sophisticated reason for that. Let's see, 2t squared plus d. Okay. All right, now let's work on the Calc 2 problem, the antiderivative of t e to the t dt. So we're going to look at t e to the t dt, and I'm going to use the table method for integration by parts. So u dv. Remember, I pick u as something that when I take derivatives of it multiple times, it eventually goes to 0. So I'm going to put a t there, e to the t there. The derivative of t is 1. The derivative of 1 is 0. So that's what I mean, eventually goes to 0 by multiple derivatives. Now over in the dv column, we got antiderivatives. Plus, minus, plus. And we see that the antiderivative of t e to the t dt is t e to the t minus e to the t plus our constant c. So let's put that in here. We have t e to the t minus e to the t plus c. Now, if we weren't given this extra information, so let's imagine that we don't have that for now, then this would be our answer. Now, often we write the answer using vector addition. We pull out the constants into their own vector. So the answer would be t e the t minus e to the t squared plus the vector c d for our constants. Now it's possible to think of this vector, or to define this vector with components c and d as a constant vector, say c, which has components cd. Remember, these two are not the same c here, because this one is a vector, this one is a number. And if that's the case, if we did that, then we could write this whole thing as like that. All right, but we're lucky enough that we do, in fact, have this extra information, so we can solve for c and d. All right, so notice here that what we found that r of t is t e to the t minus e to the t plus c t squared plus d and here we have information about what r of 2 is. So using our formula for r of 2, we see that r of 2 can be thought of as 2e squared minus e squared plus c, and 2 squared plus d. So that tells us that one way of looking at r of 2, let's see, 2e squared minus e squared, we can combine like terms to make this just e squared plus c. And 2 squared is 4, so 4 plus d. Another way to look at r of 2 is the information we have right here. Is e squared plus 5 and a 7 there. So we've found r squared in two different ways, so we can put those two different ways equal to each other, set them equal to each other. So we have e squared plus c, 4 plus d, is equal to e squared plus 5, 7. This tells us that the x and y components have to be equal, so then we know that e squared plus c equals e squared plus 5, and 4 plus d equals 7. So then we can subtract e squared from both sides. We find that c equals 5. Subtract 4 from both sides. We find that d equals 3. And so now we know that r of t has that constant for the x component and that constant for the y component. So now we've found r of t.